questions? So last time we looked at things with the normal distribution, as a probability distribution, calculating tail areas, calculating areas between points, z-scoring things, finding percentiles, and converting back to the scale. So today we're going to spend a little more time with normal distribution and using it in different ways. We're going to look at what happens when you take an average of a bunch of observations, the general case when you take the difference or the sum of a couple random variables, maybe the difference of averages. So just other ways that normal can be used to do calculations. And in that, we'll review some of the calculating the normal tail areas and things that you would use. Okay, so let's see. So normal probability distributions. So the normal distribution, right, has a mean, which we represent by that Greek letter mu, and a standard deviation, represented by this Greek letter sigma. Outlook, which uses the variance, and the square root of that standard deviation. The standard deviation is useful because the bell-shaped normal distribution for the density function is centered at the average, and areas, probabilities, are determined by how far your point is from that average in terms of standard deviation units. So if this is x, we are going to, any questions about some value of x, you're going to divide, subtract the mean and divide by the standard deviation. And most of the probability is mu plus a couple standard deviations down to mu minus a couple standard deviations. About 95% of the area under this curve, and about 95% of the probability between those limits. And there's, because of symmetry, the other 5% is split evenly on these sides. So there's about 2.5% that's below here, and about 2.5% that's above this limit. But for any other point, we're going to convert it to a z-score and look that up on a table and figure out, using logic, you need to look less than a point or 1 minus to get bigger than that point, and so on. Right? So let's look at an example. Under the standard, I guess, if you wanted to put another axis on here, for the standard normal, it's centered at 0, and this is 2, and this is -2 on the z scale. But the relative areas are exactly proportional to that. Okay, so I found an example in biometry by Sokol and Wolf. Sokol and Wolf's biometry book for at least a generation was the intro graduate statistics textbook for biology department. So particularly field biology, Museum of Comparative Zoology, and other places like that. And so it does this introductory statistics material, but it's really aimed at first year graduate students, and but it covers basically the same material. And one example in there, it concerns cockroaches. Right. And this is how long will these things survive? Survival without food or water. Cockroach doesn't seem like that humane of an experiment, but for females, it reports that they can survive about 8.5 days with a variance of 3.6. So the standard deviation would be for the females here would be the square root of that. For males, the survival is about 4.8 days. the variance of survival is reported as 4.8. The standard deviation here is the square root of that. No, it's not 4.8. That's the variance. No, the average is 4.8. The variance, sorry, I got the wrong number, is 0.9. Right. So what's the chance that a female would survive less than 8 days? What's the chance that a female survival is less than 8 days? It's going to be our question that we're going to ask to begin with. So the probability that a female survives less than 8 days, we have to z-score, right? So calculate the z-score. 8 days, they had an average of 8.5. And a standard deviation at the third is 3.6. So what is that number? On here, I started to do some calculations. I'm just going to open up another window because it's not what I had before. Wasn't exactly this one. Through your calculator, you could calculate that. Put it on this one. So I just wanted to have a different one. So 8 minus the average was 8.5, and the square root of 3.6 gives a z-score of negative 0.26. For our tables, we just need really the first two decimal places. Negative 0.26. Probability that z is less than negative 0.26. Yeah.
So what does that negative mean in this context?
In this context, so the value we have is x.
Mm-hmm.
Right? Our normal picture would have the average is 8.5.
Mm-hmm.
And this is in days. And so we're asking the question, what's the probability that this survival is less than 8 days?
Mm-hmm.
So it's less than halfway. Right? So that's why it's negative. Right?
Oh, okay.
So the z-score here is the corresponding value of a negative 0.26. So if you're thinking about this, the z-score has to be, our answer has to be less than 0.5. So if we want to find that, here's this table A, just the A column version from this. Right? Again, this only has the positive values. So that makes it a little more tricky. So we can look up the 0.26 and get 6.026. So our table says the probability that z is less than 0.26 is 0.606. Is that what it was? 0.6026. That's the information that it'll give us. That's not quite exactly what we want. We have to figure out by logic how to get that number. Here's the, we have point, a little bit closer over here. 0.26, and the area to the left of this is this 0.026. But what we really want is negative 0.26. We really want this area over here. Based on that, symmetry, the tails are the same, you flip it about 0. What's going to be that area over there?
Would be 1 minus.
Yeah, 1 minus. So 1 minus is this area, and that's also this area. This tail up here, 1 minus 0.6026, 0.3974. So this one is also here is 0.3974. form. So our answer is the probability that the female survives less than 8 days. So our z-score less than negative 0.26. This is a 6. Is 0.3974. So about 40% of them will not survive past 8 days. Yes?
Does it matter that our answers before were negative and that that one's positive? Like, is it just because it's just like a positive number in general?
Yeah, the probabilities are always going to be positive numbers. Right? So there's some area under there, some number between 0 and 1. Right? So your final answer for a probability should always be between 0 and 1. Right? And this one, like less than negative 0.26, is less than half the area, so it's going to be less than 0.05, 0.5, less than 0.5. You just have to use that logic of one side versus the other, and the tails are the same to get the answer. We could ask another question. What's the chance that, say, that a male cockroach lives less than 5 days? You write down what you'll have for the formula, for the z-score, maybe draw a picture. Then the average of these was 4.8. Standard deviation is the square root of 0.9, which is 0.9 something. I would write it down, get a calculator, the square root of 9.95, basically. Now, if you don't have your formula sheet or your calculator, there's only so far you can get. So if you're waiting, try and draw a picture that would represent this situation too. Yeah.
I have a probability of Z is less than 0.2.
It might be a little bit bigger. Oh, so Z is less than 0.0, probably. So that was, what is the z-score? How do you calculate the z-score?
So it would be 5 minus 4.8 over the square root of 0.9.
Yeah, over the square root of that, which is about 0.95. So the probability that z is less than 0.2 over 0.95, or z is less than, you got it to be 0.21. And so, is that going to be bigger than 0.5 or less than 0.5? Did anybody look that up? What did you get?
Bigger.
Bigger than 0.5.
0.8289.
0.8289? Could be. Not sure. But we will check. If we look at this 0.2, maybe not quite that big. So 0.21, right? So I'm looking across here, right, at that one.
Oh,
I'm not sure if you're-
wait, how'd you get the 0.2?
Yep. So you needed to get the kind of the 0.21. 5 minus 4.8 divided by
Oh, 0.
So 0.21 is a z-score. So again, it's kind of, we're dealing with the decimals on this chart. We're looking at 0.21. and it ended up being the 0.5832. So the math, so look at that, 0.5832 at an area. Pretty close to, so here's 5, no, the average was 4.8. And we're asking about 5, so the less than or equal to 5. So we want this area over here. In terms of a z-score, the middle's at 0 and 0.21. And the area going all the way back was 0.5832. So what's the chance that it survives more than 5 days? So a male cockroach great more than 5 days. Yeah. Any answer? Less than 5 days. 0.5832, then greater than that. Yes?
0.4168.
Yeah, 1 minus that. 1 minus the 0.5832, so 0.4168. So about 42% surviving longer. But any questions about? So we work through it one way. Sometimes drawing pictures helps to do it. Remembering that it's symmetric about the center, 50% on that side, 50% on that side. The 1 minus rule works to get tail areas. So what I've not said exactly is that survival is normal. So an important assumption in doing those calculations. Right? So in the previous, we were really assuming that the survival times are roughly normally distributed. Survival in days is normally. So that if I calculate probabilities, chances, using that normal curve based on the mean and standard deviation, that it's accurate. It very well could be. I would imagine that it's probably fairly pretty reasonable in this case. However, even if the variables are not normal, or not normally distributed, so they're something like binomial or Poisson or skewed in a certain way, maybe they have outliers. If you have a large sample size, the distribution of x bar, the sample average, is approximately normally distributed. So if we can figure out the mean and variance for a sample average, right, then we can use our normal calculations and get statements about the accuracy or likely chances of the average. And so this is saying that it's approximately normally distributed for x bar is the main result that's called the central limit theorem. And it's one of the fundamental results in probability theory and statistics that is really at the basis of most of the inferential statistics that you'll see in the published literature. Right? And it's a very useful tool. So what we're going to do is talk about x bar as a random variable. We've had random variables that are measure different things, and what this x bar does is take the average of a bunch of different random variables. The average in observations. so this is also a random variable. Things like X bar have probability distribution. Right? They have averages. You take a random sample of students and ask them how much money did they make last summer. There's an average response. But depending on who you get to sample, right, you'll get different answers. And there's standard deviations associated with X bar. Right? You have kind of a range of values. If you look at one sample of 100 versus another sample of 100 versus another sample of 100, there's some variability of those. Right? And so if each measurement, each xi, has a mean value is equal to mu, then it is the case that the expected value of our sample average is the same thing. Now this little symbol is kind of can be, it's basically saying the average of the average is the average, right? But it's the expected value, kind of the average value in terms of probability for recording the sample average across two different samples is the same as the population average. So X bar on average is the response, as if you could take an infinite sample size in the population. If each xi has a variance sigma squared, so it has a standard deviation sigma, the square root of that, and the xi's are independent of each other, then you get the response that the expectation, the variance of the sample average is related to the variance of the individual measurements, but it's divided by n. So the standard deviation of X bar is sigma over the square root of n. So that as you get bigger sample sizes and average together the responses, the variability of those averages goes down. Take a very, very large sample. It's almost going to be very, very close to the mean mu. And it doesn't have much room to deviate. You take a random sample, you get some big ones, some small ones, a bunch of them in the middle, and you merge them together, and the small and the big kind of cancel out. And the bigger the sample is, there's more canceling of those extremes, and it becomes more centered right around the data. And the third bit that makes this extremely useful, that is if the sample is relatively large, the sampling distribution, the probability distribution for X bar is approximately normal. So large N, the probability distribution X bar is approximately normal. Which is a great simplification. So if you had 100 observations, and they all come from something that's Poisson, it's a very complex and tedious way of going about figuring out what the distribution of a sum of Poissons or an average of Poissons actually is. There's an actual probability distribution that's very complex. But it looks quite normal, and if we just use this normal approximation to it, we can actually do calculations that are quite accurate. Right? So in this example, so for this, continuing with this lovely cockroach example, let's say that for the females, the averages are 8.5, and the standard deviation or the variance was 3.6, and for the males, the average was 4.8, the variance of 0.9. Standard deviations, then the square root of that, 0.95. The square root of 3.6 is what? It's the square root of 3.6 is just 1.9. Right? So it's 1.9. And let's take a sample size in each group of 10. We can ask things like, what's the probability that the average for the females, if F1, F2 are the survival times for these different females, what's the average survival time, is something like less than 8. So average survival of n equals 10 females. And this is what the chance that the average survival is less than 8 days if the population of individuals had an average of 8.5 and a standard deviation of 1.9. So what this normal approximation says is figure out the standard error. Standard deviation for 1 is 1.9, or the standard error, sigma over the square root of n, is we take the 1.9 divided by the square root of n for females. For males, it'll be the 0.95 over the square root of 10. And those calculations, so 1.9 divided by the square root of 10 is 0.6, 0.95 divided by the square root of 10 of 0.3, so 0.6 and 0.3, when we do those, so we expect an individual measurement to be kind of plus or minus 1.9 or twice that 3.8 away from 8.5. Once we average together 10, we don't expect the average to be more than kind of 0.6 or maybe twice that 1.2 plus or minus. Right? The average of 10 is going to be almost certainly closer to that. So now we ask a question about the average. What's the chance the average is less than 8 days? It's a normal problem. So z-score. So we're going to z-score. Now 8 is our number. We just subtract an average. If these are all females, average is 8.5. But now we don't divide by 3.6. We're going to divide by the new standard error that's sensitive to the sample size, 0.6. And so this is probability that z is less than negative 0.5 over 0.6. That's probably that z is less than negative 0.83. And we have to figure it out from the table. Blue to go away. Now you're going to have to look up some number, like some x number. If you only have the positive ones, you have to look up 0.83. $7,967. So we can look up there's 0 on the z scale. We can look up 0.83, which gives us area of 0.7967. But we want the probability that it's less than negative of the 0.83. So what's the?
1 month.
1 month.
7.
You both have it. 7,967. Take the minus that, so 0.2033 is a chance you're above that. It's also the chance you're below the negative. There's that tail and this tail in a real picture should be equal. So 1 minus 0.7967 would give us 0.2033. That's about 20%.
Can you explain like what the original question is.
Yep, so the original question is, what is the chance that the average survival in 10 female cockroaches is less than 8 days?
Okay. And that you wouldn't just assume based on the average that's given, like you have to do all, so you're finding standard error basically?
Yeah, so you're changing from using 3.6 as a variant, or 1.9 as a standard deviation. If it's a question about the average, then you change it using 0.6 as a standard deviation. So instead of asking about one person, or one cockroach in this case, right, when we did it before, right, we did one, what's the chance that one female cockroach survives less than 8 days?
Alright.
So one female had, it was about a 40% chance of surviving.
Yeah.
But now you have a bunch of individuals and averaging them together. So the average tends to stay closer to the average of 8.5.
Okay.
So the chance that the average is much less is less, right? So they're more likely to be close to 0.8.
That makes sense.
Thanks. Yeah, so there's this distinction between one person in the population and then the average of a bunch. And the average of a bunch, even if the distribution underneath of it wasn't normal, right, tends to look more normal. And that's called a simple limit. Yeah. Let's do one more example. So let's say we have 10 male cockroaches. What's the probability that the average survival time is, let's see, so there, a pretty small standard deviation, is less than 4. Average survival time is less than 4 days. Well, the average is 4.8. So when we z-score that, we still are taking 4 minus 4.8. But now, because it's the average of 10, we divide the standard deviation by the square root of 10, because the averages are more precise. So we divide by 0.3 instead of the other 0.9. It's smaller. So this is the probability that z is less than negative 0.8 over 0.3. That's the probability that z is less than negative 2.67. 2 2/3. So when it was 1 cockroach and the standard deviation was 0.6, that wasn't so far away. So that's 1.5. But now, because we're averaging 10, the chance that you get an average of 10, to produce an average of 10 that's really small, you have to have a lot of small, short survival times in this case. That's just pretty unlikely. So this one, if you look at 2.67, there we go. So 2.67 is all the way over in this column. 2.67 is 9962. But that's less than that. We need the tail area. So 1 minus 9962 is going to be our answer. 1 minus 0.9962, so 0.0038. And if this had been an average of 100 cockroaches, it almost certainly never would have happened, right? The probability would be even smaller because the standard error is going to go back, be decreased even further by averaging more together. So that's the application of this central limit for doing things, right? Another place that this gets used is that in the binomial distribution. Is that the binomial is discrete. It takes on values 0, 1, 2, up to n, the number of successes out of a certain number of trials. And the probability that is given by a probability formula. But if n is large enough, then even though there's probabilities only at certain points, the kind of shape of all the probabilities, the masses of probability among points, around where it has much probability looks very normal. So you'll have some probabilities at different points, but for large values of n, here's the probabilities, I guess that's called k, but they look pretty normal. And what it says is you can approximate probabilities by not necessarily adding up all those little points in there, probabilities, but instead doing a normal calculation. What do you use for the normal? You need a mean and standard deviation. So it says you can use mean, n times p, and you can use a variance. There's the generic cases, I'll put the same order here. The binomial formula for variance is n times p times 1 minus p, and sigma squared. For the standard deviation, you take the square root of that, np 1 minus p square root, and you get sigma, right? Standard deviation. So any question you ask about binomial, you can now convert it to a normal, and answer it with less. It's not really a problem anymore. Calculators and computers do pretty amazing things, and it's pretty accessible. You can install. I don't know if you can install R on your phone, but you probably can get some things on your phone that can do these calculations. But let's look. Let's say that at the rate of having cesarean sections, C-sections in birth is about 32%. And we have 1,000 births. You can imagine these are singletons, unrelated. So reasonably clear that they're independent of one each other, whether or not necessary in section or not. What's the chance that you would have less than or equal to 350 during the year? Say this is during a year period. Less than 350 women would have cesarean sections out of this group. This reasonably well fits a binomial situation, right? Binomial n equals 1,000, p equals 0.32. If we're actually doing it with binomial, we would have to add x going from 0 to 350, 1,000 to x, 0.32 to the x, 1 minus that to 1,000 minus x. We'd actually have to add up 351 terms to do that calculation. You can do that in R and add them up. It's pretty fast, but it's just one. It is this summation. For the distribution of x, because it's a sum of things, it's not exactly an average, but it kind of works the same way basically. That the number ends up being approximately normally distributed. But to use a normal, we need a mean and variance. What's the average? N times p. So if it is 32%, right, then it's 1,000 times 0.32 or 320. The standard deviation in the 1 minus p square root. So 1,000, 0.32, 0.68, square root of that, 0.14, 0.75. And you can leave that as a decimal. You don't have to change it to integers or anything like that. 14.75 births, but leave it as a decimal. So we can answer this question approximately by z-scoring it. 350 minus how many we expect under the binomial model. 320. And divided by the standard deviation for this one. 14. This is the probability that z is less than or equal to I don't know. Part of it, yeah. We'll shift over to R to do this one. So the 350 minus 3, I'm not going to use that other stuff. 350 is what we asked about. 320 is the mean. And 14.75 or so is the standard deviation. So we're looking at a z value of 2.03. So the chance that z is less than 2.03. That's directly what's in the table. So if we go to our table and find the x value, 2.03, right in this column here, 9788, 97.88%. That's a direct question, 0.9788. Almost 98% of the time, you're going to have 350 or less. So if you're ordering supplies and things that this hospital would need, you're going to have 1,000 births and about this many cesareans are expected. If you plan for less than 350, you should have enough supplies to cover the situation about 97.88% of the time. Yes?
So the last question was different because it was asking like the average, like what's the probability of the average being
Yep.
a certain number?
Yep.
Okay. And then this is like the probability of an exact like value.
Yeah, so this is particularly key to the binomial.
Yeah.
As a specific instance of binomial, so we use the binomial mean, binomial standard deviation.
Mhm.
And the other one, you have these quantitative measurements that have an average and a standard deviation. When you average those together, you calculate that the standard error is over square root of n, and it's another normal calculation.
Okay.
But we'll see some more examples of these as we go along and try to keep that straight, particularly review problems as well. Is it about just one observation or is it an average? Is it a binomial model? You know, figuring out which formulas to use for that. But again, once you figure out what type of problem it is, it follows a lot of the same pattern.
Mhm.
Now, R has some facility built into it. That's our z-score. It has a command called pnorm. This is calculating the probability you're less than a certain value. So if you put 2.03 in there, it calculates the probability you're less than or equal to 2.03 under a normal. It's called a cumulative probability for a normal. P-norm. There's a few different things that we'll do for a normal. The p-norm is the one that calculates the probability less than a value. Yes?
Would it work for negative values?
It works for negative values. So if the average was 320, so the average was 320. So expected value for this binomial was n times p was 320. We had asked about 350. Now if we kind of go the other direction, 30, because it's symmetric. The chance that x is less than or equal to 290. Again, it's a z-score. Well, if you z-score that, it's going to end up being negative 2.03. So 30 above translates into 2.03. So 30 below translates into the negative. And then that is going to be 1 minus the 0.9. Number 9788. 9788. So 0.0212. So it should work for negative numbers as well, plus or minus, above or below the average. So in this normal command, right, if you had negative 2.3, it'll give you 1 minus that probability. So 1 minus that one gives you that other tail area. Yeah. Now, R is flexible. You can actually give it a mean and standard deviation, so you don't have to z-score it at all. But it's always good in your mind to be able to z-score and figure out what's going on. So we typed in p-norm. We asked first about 350, but if the average is 320 and the standard deviation was 14.75, it takes the arguments in the order listed there, so it assumes that's mean standard deviation, and it will give you this. That was pretty close. It's carried a few more decimal places, so it's just a little bit different, but it's about the same as that. So for some things in R, on the homework, if you have to calculate normal things, you can do it this way. I suggest practice looking things up in the table, because on an exam I can give you the table, but you certainly can check your answers. And if you do things precisely, you might be off by a little bit in terms of the decimal places. That won't be a great difference one way or the other for the accuracy you're dealing with, but it's more the concept of doing those things. But any question? So, what is good for sample size? So, sample size for binomial, or normal approximation to binomial. How many trials should you have before you go to doing this? Generally, you want an adequate number of sample sizes, so there's enough points there. If you only have 5 trials, your outcomes are 0, 1, 2, 3, 4, 5. That's not going to be very continuous. It's not going to be close. If you have 500, that's probably going to be a lot better, because there's 0, 1, 2, there's 501 different possibilities that spreads the probability over. So you want n large, but p plays a role in this too, right? So if p is 1/2, half the times you're small, half times big, and it's not clustered at one edge. But if p isn't at 0.995, you almost get all successes. You're stuck at n minus 1, n minus 2 out there. That's not going to look normal if it's really clustered at one side. Same thing, if p is 0.001, you're going to have 0, 1, 2, 3. You're going to have everything's down there, and it's not going to spread out at all. So that gets, so p not too extreme. And so one way to look at that is n times p times 1 minus p greater than or equal to 5. Some books say n times p times 1 minus p greater than or equal to 10. So kind of somewhere in that range, it gets kind of depends on how accurate this approximation you want it to be. The bigger n, the bigger that is, the better. But and if it's way past that, at 20, 30, 100 or more, it's going to be great. So we could examine that a little bit by just making some plots. In R, you can make a plot. Let's say x goes from 0 to 10, and we'll do, we want to plot x and then the density of a binomial for the numbers 0 through 10. 10 trials, probability 0.5. Right? Although that looks nice and symmetric and things, it's pretty chunky and might not work quite as well. If p was skewed as well, it's less than, here's 0.3, not very, normal of looking like. If you imagine a normal tail, there's not enough out here, it's kind of a little skewed, and it's not going to work so well. As you make that smaller, normal probabilities aren't going to be too accurate there. On the other hand, if x goes something like 0 through 100, and we have 100 trials here, That's kind of what the probabilities look like for 100. This part in here is the probabilities in here if you put a normal curve over that, and instead of adding up the heights at each of these points, but did a normal area under the curve. It's going to be pretty accurate. So 100 times 0.2 times 1 minus that is 16, and that looks like a reasonable curve. The chance that you're above, say, 35 or 40 is practically zero, you know, under both. The book mentions one thing called a continuity correction. That's kind of a technical thing. And the fact here with this binomial one is we're going from something that's discrete, right, at integers, 0, 1, 2, 3, to something that's continuous, right, through the entire real number line. Right? And the conceptual idea is that if you have just a few blocks of probability here, they only side by side. You have just a few blocks of probability here for a binomial. And you're going to try and calculate those areas. You're going to add up those areas. You're going to add up these areas here. Let's do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 trials. And you want the probability that x is less than or equal to 6. Well, this isn't going to be a great one for approximation anyway, because it's just too small. It's just too discrete. If you do a probability that a normal is less than or equal to 6, well, the block at 6, the value of 6 might be thought about right here in the middle. So if you do the probability at 6 and less, right, you kind of taken half that block. Right, so if you do it at 6, you're kind of doing kind of half, you get kind of half that block. So it'd be a little bit low. So this continuity correction says if you want less than or equal to 6, try using the normal less than or equal to 6.5. Add a little bit more in to try to capture that little extra piece. Makes a small difference with small sample sizes. And so then your z-score here is going to be 6.5 minus the mean over the standard deviation for a binomial. And that'll be a little bit closer to the actual binomial probabilities. So I don't know that there's a huge gain in the accuracy that you would get in real problems. Hopefully you'd have large sample sizes. Or you'd be able to do the exact binomial calculations. I mean, with computers, you know, why not? You can do that. But there's a concept here that we're going from something that's discrete, that's not normal at all, it's not even continuous, but we're pretty well able to approximate it by some continuity one, a continuous one. And so there's a little bit of insight maybe to think, oh, there's actually a little bit of difference between the discrete ones and the continuous ones. But as sample size gets bigger, they kind of go together. And the single limit theorem takes on. And it's a pretty powerful result. Any questions? So we'll stop there. And see you on there. Yep, so we kind of the z-score that's up here at 97.5. Yep.
And probably 5%.
If you want the 5th percentile, that'll have 5% down below it. So if you look up the Z-score for 95%, that one that has 95% below is 5% above. That's about 1.64, 1.65, something like that. And that's 5% above. So the negative 1.64 will have 5% below. Alright. Yes.
I wouldn't Yarn Friday
Oh.
or zoning candidate.
Yes, I do. Yana?
And also,
Yeah, it's because we
yeah, mention on the chart as well as
Yeah, the normal chart. This is
Yeah.
the-
I think that you're important.
That's a handout, and then
Thanks.
the chart that's in the back of your book actually has 4 columns to it and different
Okay.
pictures, but that's really enough to get
Thank you.
everything. Yeah.
And then you
So I
just-
have a question on the board.
Yes.
Okay, so I started a 5.2 before.
Okay.
Now, it's that one's comparing different countries and ages for the compliance part of it, and
Okay.
I started today, so would that be, I wouldn't be doing that, just taking the difference in age.
Mhm. Difference in ages.
So I think I did it wrong as far as multiplying, I had to finish up.
Was this 30? I don't remember exactly.
What do you have?
So it's 30 years is the
Yeah.
difference. And the standard deviation.
And then I would use the new formula we just got today where it's
Yeah.
very, okay. All right, and then for 5.23, I was pretty fine with these. For the 5th percentile, I would just do it normally, then subtract 1. How would I?
Yeah, so you want to define the 5th percentile.
Mhm.
So you want some point that has just 5%.
Yeah.
And what we can find in this A chart is the point that has, 5% above.
Okay.
So if you look, that's going to be about 95%
Yeah.
below. So if you look for the 0.95, it's kind of around here, about 1.64 or so.
Okay. Uh-huh.
So the 5th percentile is going to be negative 1.64
Mhm.
for the Z value.
Yeah, that's for Z value?
Yep.
Okay. And then you would just do the inverse of that?
Mhm.
Okay, great. Thank you.
Yep. How are your other courses going?
Good, good. It's been kind of this whole exam month for me,
Yeah.
so, yeah, it's okay though. It's almost done. Today's like the last, this week's the last push for it.
Yeah.
And then I have like a small draft for the war piece, which is not
Okay.
good.
We kind of do 4 homeworks and then an exam.
Yeah.
4 more homeworks and an exam. So
Yeah.
we're kind of in a building, wanting to building up some more material.
Yeah.
And then we'll do review for that exam and some study problems. And
Yeah, that's good.
kind of break it up.
Oh, yeah, of course. Okay. Have a good day.
Thank you.